Hello everyone, my name is Samuel Williams and I'm super excited to be able to share my work on the new Ruby Fiber Scheduler today. In this talk we are going to show that blocking operations are often detrimental to the throughput of your applications and how non-blocking event-driven I/O using fibers can improve concurrency. We will then look at how the new Fiber Scheduler can improve existing applications with minimal changes. Right, let's get started. Is Ruby fast enough? A huge amount of work goes into making the Ruby language faster. We have implementations in C and Java using techniques like just-in-time compilation and the compacting garbage collector. Yet, we are still trying to improve performance. It is a very important goal to increase customer satisfaction and reduce business costs. Let's consider this hypothetical network request. The blue part is 10 milliseconds of work done by the actual Ruby interpreter executing instructions to handle the request. The green part is 190 milliseconds we spend waiting for the network. The total time is 200 milliseconds. This is a very typical situation in I/O-bound applications, such as database queries, where you send the query to the server and wait for the results. If you send a very complicated query to a large table, it could even take several minutes, and you might generate many rows of results which you need to read back. HTTP requests over the internet are often very slow, easily 100 milliseconds or more. Requests which involve a lot of data across a slow connection can take hours, with the vast majority of that time just waiting for the network packets. If you don't believe me, here is an example of a web application which has a similar profile. At its peak, 25 milliseconds is spent executing Ruby code, and 150 milliseconds is spent waiting on Redis and external HTTP requests. So, what happens if we make Ruby 10 times faster? In our hypothetical request, we reduce the time spent processing the request from 10 milliseconds to 1 millisecond. That's a 10 times improvement. But the total time is still dominated by the waiting, which hasn't changed. What about if we could make Ruby execution 100 times faster? Surely that's got to help. Here is the result. It should be obvious now, even if we improve the performance of Ruby, there is still so much time being wasted by waiting. So, how do we make Ruby faster? What can we do to avoid waiting so long? Let's take our example of a single request and look at it in the context of a small program. Here is our single request, and in our application it's one of many. This kind of sequential processing happens everywhere, on clients interacting with multiple remote systems or fetching multiple records, or on an application server handling many discrete incoming requests. What if we could change this, so while we were waiting for one request to complete, we could start on another? While the latency of the individual requests cannot be changed, we can greatly reduce the total latency of all the requests together and improve the application's throughput. So, how do we build this? Let's take a look at how we need to change the code. Let's start from our sequential program. Firstly, we are going to add a worker to wrap our request so we can represent individual jobs that can run concurrently. Now, let's expand what a request looks like. First, we are going to make a connection to the service. Then we are going to write a request. Finally, we are going to read the response. Okay, let's make our read operation non-blocking. Firstly, we are going to change read to read non-block. Then we need to check the result, and if the data was not available, we will get the response wait readable. In that case, we will use a special system call, io.select, which waits until the data is available. This is the operation which accounts for the waiting time in our program. Rather than waiting, we can use another special operation called yield, which passes control out of the current worker and allows another worker to execute. We also store the current worker into a waiting table indexed by the I/O we are waiting on. Finally, we implement an event loop, which waits for any I/O to become ready using io.select, and then resumes the matching worker so it can continue processing the response. Congratulations! This is the entire implementation of non-blocking event-driven I/O for Ruby. As you can see, the implementation is a bit verbose. We don't want developers to have to rewrite their code like this because it exposes a lot of details that they shouldn't need to worry about. In fact, it's my belief that you should not need to rewrite code at all. Scalability should be a property of the runtime system, not your application code. So let's rework this code and hide some of the details behind a tidy interface. Firstly, let's encapsulate the waiting list into a scheduler object. This scheduler will provide the interface required to wait on I/O and other blocking operations, including sleep. We will use it to hide all the details of the event loop and the underlying operating system. Next, let's move the details of waiting on a specific I/O into the scheduler implementation. There is already a standard method for doing this called waitReadable. This allows the scheduler to handle the scheduling of individual tasks without the user needing to explicitly yield control or manage the waiting list, as these are usually implementation-dependent details. Finally, we move the entire event loop into the scheduler implementation and replace it with a single entry point, run. Because some operating systems have very specific requirements on how this loop is implemented, putting it into the scheduler improves the flexibility of the user code to work on different platforms. As I said earlier, I don't believe we should need to rewrite existing code to take advantage of the scheduler. Other programming languages require explicit syntax, such as async await, in order to do this. But we can take advantage of Ruby's fibers to avoid this explicit syntax and hide the await in the method implementation. In our code, we expanded the read operation to become non-blocking, but this detail can be hidden within the implementation of Ruby itself. Let's revert the implementation back to the original blocking read. We still need to call into the scheduler. How can we do this? In our implementation, scheduler is a local variable. However, we introduce a new special thread local variable to store the current scheduler. The thread local variable allows us to pass the scheduler as an implicit argument to methods invoked on the same thread. The Ruby implementation of io read is largely the same as our non-blocking implementation earlier, and internally it invokes RubyIO wait readable. It is in this method that we add a little bit of magic. At the start of this method, we check if a thread local scheduler is set, and if it is, we defer to its implementation for wait readable. This allows all blocking I/O operations to be redirected to the scheduler if it is defined, and without any changes to application code. Finally, we have not revealed the implementation of worker. It is in fact nothing more than a Ruby fiber. While the practical implementation has a few more internal details, this is, essentially, the entire implementation of non-blocking event-driven I/O for Ruby. The original concept for this design was started in 2017, and finally in 2020, after testing the ideas extensively, we made a formal proposal for Ruby 3. This design specifies the scheduler interface which can work across different interpreters, including CRuby, JRuby, and TruffleRuby, and how the existing blocking operations should be redirected. The actual implementation of the scheduler can be provided by different underlying implementations, which allows for great flexibility. This proposal included a working implementation for CRuby, and it was recently approved by MATS for experimentation in the master branch. This represents a great milestone for the project. We hope to iterate on the current proposal and deliver a solid implementation for Ruby 3. How do we support existing web applications? Fundamentally, the scheduler is designed to require minimal changes to application code. However, we still need to provide the model for executing application code concurrently. In addition, not all blocking operations are due to I/O. This is especially true for the current database gems, which sometimes hide the I/O operations. Even though there are challenges, because this is a very exciting development, we found existing maintainers were willing to start making the necessary improvements. For applications that want concurrency today, you can use Async. The core abstraction of Async is the asynchronous task, which provides fiber-based concurrency. We introduce new non-blocking event-driven wrappers with the same interface as Ruby's I/O classes. In many cases, you can inject them into existing code and things will just work without changes required. In Async, tasks execute predictably from top to bottom, so no special keywords or changes to program logic is required. In the case of Ruby 2, you must use the async wrappers, but in Ruby 3, the scheduler interface allows us to hook into Ruby's blocking operations without any changes to application code. At the core of Async is the non-blocking reactor, which implements the event loop. It supports a variety of blocking operations including I/O, timers, queues, and semaphores. Blocking operations yield control back to the reactor, which schedules other tasks until the operation can continue. The async gem is less than 1,000 lines of code, with good unit test coverage. We felt it was very important to reach a stable 1.0 release with a well-defined interface, along with a good test suite, because this provides a strong foundation for reliable applications. Lately, I've been looking into Async, as one of my projects would really benefit from non-blocking I/O. It is really beautifully designed. Janko Moronic on the general design of Async. Async has a growing ecosystem of scalable components, including support for Postgres, Redis, HTTP, and WebSockets. One of our goals is to bring high-quality implementations of common network protocols to Ruby, with a focus on both consistency and scalability. Almost all the components are tested for performance regressions. Because the Ruby 3 scheduler interface has been merged, we now have experimental support for that interface in Async. Once this interface is finalized, you will be able to make existing Ruby I/O non-blocking when used within an async task. Right now, it's experimental, but we hope to release it soon. If you write existing code with Async, you will not need to make any changes to see improved concurrency with Ruby 3. One of the most critical parts for many businesses using Ruby is the Web Application Server. We built Falcon as a scalability proof of concept, and it was so successful that we've continued to develop it into a mature application server for Ruby web applications. Falcon is implemented in pure Ruby, yet in performance, it rivals other servers which have native components. This reinforces our original assumptions about the diminishing returns of improving the Ruby interpreter. Out of the box, it supports HTTP 1, HTTP 2 with zero configuration. This gives you a modern localhost development environment. It can also be used in production without Nginx. It has a really great model for WebSockets, and we recently demonstrated a single instance with 1 million active WebSocket connections. In order to reach this level of scalability, it uses 1 fiber per request, which means that your application requests will be scheduled concurrently if they do blocking operations, for example database queries, web requests, Redis, and so on. To achieve parallelism across multiple CPU cores, Falcon uses a hybrid multi-process, multi-thread model, so we can support CRuby, JRuby, and Truffle Ruby seamlessly. So, is it scalable? Well, like anything, it depends on how you use it. But in various micro benchmarks, we have shown that it can perform very well, especially when there are operations which are non-blocking with Falcon but blocking on other systems. This graph shows Puma versus Falcon. Puma plateaus at 16 workers, while Falcon is able to continue scaling up until all CPU cores are pegged. We thought this was a great result, especially if your company is dealing with a high volume of traffic. Async is the right model because web applications are almost always I/O bound. The Ruby web ecosystem is really lacking in scalability, for example WebSockets on Puma. Async unlocks the next tier of scalability in the most Ruby-like way possible. Brian Powell on migrating from Puma to Falcon. So, the big question, does it work with Rails? Yes, it's rack compatible. However, there are some caveats which we will discuss next. ActiveRecord is a commonly used gem for accessing databases. Unfortunately, ActiveRecord currently uses 1 connection per thread. Because of this, multiple independent fibers on the same thread will be using the same underlying connection. This can cause problems, because multiple fibers could incorrectly share a transaction. This is kind of a design fault of ActiveRecord, and there is discussion happening right now about how we can improve the situation. I think Ruby 3 will drive these changes as the model for event-driven concurrency becomes clearer. Another issue is that database drivers don't use native Ruby I/O, and are instead usually opaque C interfaces. However, the maintainer of the Postgres gem is interested to add support for non-blocking I/O. I believe we will see expanded support from other maintainers once Ruby 3 concurrency model is stabilized. These changes should percolate up into the higher level libraries and hopefully drive adoption. As an alternative, we recently started implementing a low-level database interface gem called DB. It currently provides non-blocking Postgres and MariaDB MySQL access. While we believe the existing gems may eventually adopt the event-driven model, we didn't want to wait for our own code. Redis is another commonly used system for fast access to in-memory data structures. It is commonly used for job queues, caches, and other similar tasks. We introduced a PR to support event-driven I/O in Redis RB, but unfortunately, it was rejected. So we have continued to maintain the pure Ruby Async Redis, which is almost as fast as the native High Redis implementation. One important point about the async gems is that they are guaranteed to be safe in a concurrent context. In our research, we found that many gems are not thread safe, including up until recently the Redis gem. HTTP is a key protocol of the modern web. As such, we provide a gem, Async HTTP, which has full client and server support for HTTP 1 and HTTP 2, and soon we hope HTTP 3. This gem fully supports persistent connections and HTTP 2 multiplexing in a completely transparent way. That provides great performance out of the box when combined with Falcon. We recently added support for Faraday with the Async HTTP Faraday adapter, and we tried it out on several projects. The GitHub changelog generator makes many requests to GitHub to fetch the details about a project. While we didn't work on all areas of the code, we saw a significant performance improvement by fetching commits and pull requests concurrently. For bigger projects, the improvements brought about by multiplexing and persistent connections are even more significant. In another script, a traditional HTTP gem was compared to Async HTTP Faraday when fetching the job status of a large build matrix from Travis. I think it was about 60 to 70 requests in total. Because those requests could be multiplexed on a single connection, the overhead was significantly reduced. Rather than making a large number of requests sequentially, all the requests could be made on a single connection. It's these kinds of results that make me personally really excited about the future of Async, Falcon, and non-blocking event-driven Ruby. As a bit of fun, I found this interesting experiment with the FFI gem, which we use for implementing the DB drivers. It moves FFI calls to a background thread, and then yields control back to the scheduler. While it's pretty risky in general, in some cases this can be a valid approach, and offloads otherwise blocking C functions to background threads. So, what are the next steps? It depends on you. The community. Please try these new gems and features of Ruby and give feedback. The best thing you can do is have fun with these new projects. I hope they make scalability exciting. And the businesses, please support this important work. We recently introduced a paid model for Falcon. If you are interested in this, please reach out. We want to support the Ruby ecosystem and help it continue to grow, especially in relation to scalability. If this is important for your business, you can help us develop it further by investing financially. Thank you for listening to my talk. This brings us to the conclusion of the presentation. Next, we will have a live coding session with questions and answers.